Hello, geometry students. Today we're going to be covering the Unit 7 activity. It has to do with coordinate geometry. This one's a little tricky, but we're going to go through it, and we're going to go through it kind of slowly. So if you want to turn me on 1.5 speed, I think you could do that if you're getting it right away. Anyway, let's go ahead and get started. I'm going to share my screen with you guys. All right. So I'm starting looking here on page 5 of the activity, area of a triangle. Like always, I'm going to read aloud, and if you guys can follow along, that'd be great. Finding the area of a triangle is straightforward if you know the length of the base and the height of the triangle. But it is possible to find the area of a triangle if you know only the coordinates of its vertices. In this task, you'll find out. Consider a triangle ABC whose vertices are A, B, and C, there, 2, 1, 3, 3, and 1, 6. Let line segment AC represent the base for the triangle. Okay, so what I would suggest first is let's go ahead and pull up another tab, and we're going to go on GeoGebra here, all right? Now, you can go on this website, pull up a separate tab, go to geogebra.org, and I like the classic. So geogebra.org/classic should look exactly like this. We'll have the same tools on top and everything. But we're going to go ahead and graph those 3 points. The 3 points A, B, and C that we saw before. So A is 2, 1. I'm going to write them down. B is 3, 3, and C is 1, 6. Okay, and I'm looking at that right here. Okay, so A is 2, 1. So first we're going to go on GeoGebra, look at the point tool. Let's go ahead and put the point tool, click point, and we're going to look at point 2, 1. So that's right here. Notice it gives us an A. That's good. B is 3, 3, and C is 1, 6. Now I want to form this into a triangle. So on the toolbar, go to the Polygon tool, which is right here, Polygon, and you click, 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 and then back to make the triangle. So now we have triangle ABC as shown. Now it's wanting us to say that AC is the base, okay? Because it says, let line segment AC represent the base of the triangle. Find the equation of the line passing through B and perpendicular to AC. So passing through B and perpendicular to AC. So here's AC again, and I want a line that's perpendicular to that and passes through point B. So on our toolbar, you can go to this tool right here. This is the perpendicular line tool. Click that, select a point, so select point B, and then select this segment. So what's produced is this line F, and if you notice, F is perpendicular to AC, meaning it crosses AC at a right angle. You can see that's a right angle there between AC and this line F. And it passes through point B, so that's good. What they want is the equation of this line here, the equation of this line here. If we zoom in, you can see it passes through 2.4. You see that? 2.4. And what's the slope of this line? Well, let's go ahead and look at a couple points. I would look at this point and this point here. It's a random, I'm picking a point on this line F, and it's easy to see where it is. And you can see this point is at 8, 4. So in order to find what the equation of this line is, all we need to do is find the slope and the y-intercept. So the slope, and if you recall, y equals mx plus b is typically how we write the equation of a line, where m is the slope and b is the y-intercept. I know you guys covered this in Algebra 1, and I know this is geometry, so you may not you may need a bit of a refresher, but the slope is the rise over run between 2 points. So between any 2 points on here, we want to do the rise over the run. And that's why I picked a point here, because now I can easily see what's the slope between this point and this point. The rise is 1, and the run is 1, 2, 3, 4, 5. So our slope is up 1 over 5. So our slope, our m, is rise is 1, run is 5. So our slope is 1/5. So our equation is y equals 1/5 x plus, and then the b is the spot where our line crosses the y-axis. So as you can see here, our b is 2.4. Our y-intercept is 2.4. 2.4. Whoa. 2.4. Great. So that's it. That's the equation of this line here. It's perpendicular. It's perpendicular to line AC, and it goes through point B. So I want you to go ahead and put that right here using the equation editor. So you can use the equation editor here. And let's go ahead and do that. So it'll be y equals mx plus b. In our case, that's going to be y equals 1/5 x. So I'm going to do this fraction here. 1/5 x plus, and our b was 2.4. Just like that. Okay, not too bad. Let me zoom in a little bit, make it see that a little better. Okay. Let the point of intersection of AC with the line you found in part A be point D. Find the coordinate for point D. So you see how I had another point over here already, point D. I'm going to actually delete that one. I no longer need it. So I'm going to go ahead and right click on this, and I'm going to delete this object. And instead, I'm going to put another point, and I'm going to put it at this intersection between AC and this line, F. Okay, and it's point D. What they want to know is what's the coordinates for point D. And as you can see, our coordinates for point D are 1.65, 2.73. So our coordinate point D is, wait, what did I say? 1.65, 2.73. Let's move on. Use the distance formula to find the length of the base. Okay. So what we want to find, length of the base. So we want to find the distance between A and C. The distance between A and C. And they want us to use the distance formula. So what I want to kind of show is, well, let me show you on this here. So we have where A is. A was at like 2, 1. And C was at 1, 6, I think. Yeah. And what we want to find is the distance between here. We want to know, what is this distance? Again, this is A, and this is C. Well, what we can do is we can draw a triangle here, essentially. Okay. And this is actually a right triangle. A right triangle. And we're missing this side length. In this case, it's the hypotenuse of this right triangle. Now, if you recall, how do we find a missing side length of a right triangle? Well, that's the Pythagorean theorem. A squared plus B squared equals C squared. Okay. Now the C is the hypotenuse, the longest side. In our case, we'll put that as D for the distance. What's the distance here? And what's the distance here? That's what we need to know. Well, let's go back to our GeoGebra and we can see. Here's A and here's C. So what's the distance here between them? You just imagine there's a triangle there. Hopefully you could kind of imagine that, where this length is the hypotenuse. So this length right here is 1, right? Because it goes from here to here. So that length has a length of 1. Whereas this length has a length of 1, 2, 3, 4, 5. 5. So in our Pythagorean theorem, our A and our B will be 1 and 5. It doesn't matter which one's A and which one's B. That part doesn't matter. So that'll give us 1 plus 25, because 1 squared is 1 and 5 squared is 25, equals D squared. 1 plus 25, that's 26, D squared. Now, to get rid of the squared, you use the square root. Square root. So the distance is the square root of 26. Square root of 26. And you can use a calculator to get that as a decimal if you like. It's going to be close to 5, a little bit more than 5. And square root of 26, and that's 5.1, we'll say, approximately. Okay. Hopefully that kind of makes sense. So I want you to show all of this work using the equation editor, okay? And that's using this. So our first step was that a squared plus b squared equals c squared. And to do a squared, you can click on this tool right here, and it kind of gives you the exponent there. And then to get out of the exponent, I use the right arrow, or you can click to the side. A squared plus b squared. I guess clicking to the side doesn't work. You have to use the arrow, I guess. Equals c squared. Whoop. And then the next step was that a is 1. B ended up being 5. And we're going to use the letter D for the distance. All right, and then so on and so on. So dot, dot, dot. I want you to finish the rest of this, show all the work. Basically, I want you to show all of this on that equation editor. Make sure you show all your work for full credit. Right, so do the rest of that. Once you're done, you'd press OK. I didn't show the full thing, but I need you guys to do the full thing. Now we need to find the area of triangle ABC. So in order to find the area of that, we need the base, but we also need the height here. We also need the height. So we can use GeoGebra to find this distance here. In order to do that, let's go ahead and I'm going to go to the segment tool, segment, click B and D, and it'll create this segment G. From there, you can go on the tools and right here, click on distance or length. So I'm on this angle tool and down here on distance and length, click that, then click that. So it gives you the length of this segment between B and D. And we already know the length between A and C. It was 5.1, if you recall. Now we can find the area of that triangle. The way we do that, for the area of a triangle, the formula is 1/2 base times height, just like that. So in this case, our area is going to be 1/2. And the base was AC, which we determined earlier was 5.1. And the height, we're using BD for that, which according to GeoGebra is 1.37. Now we just need to multiply these together to give us our area. This will give us the area of the triangle. 1/2 times 5.1 times 1.37. And we get 3.49. So this is the area of the triangle. I want you to show this work on the equation editor here. All right. Now check your work by using the GeoGebra geometry tool to represent parts A through D. Open GeoGebra. Okay, we already did that. Blah, blah, blah. Perpendicular, blah, blah, blah. Take a screenshot. Okay, so you want to take a screenshot of this. I'm going to actually get rid of this line. The line segment between BD should still exist, but I'm going to get rid of this segment. I'm going to not show object. So we need to take a screenshot of this. So we're going to use our snipping tool, take a screenshot, copy, and hopefully it'll paste. Of course it does not. That's okay. What you can do is when you have your screenshot, you can save the image. Save the image. And then on right here, insert image, you'd insert image. And then wherever you saved it, you go choose file. And then wherever you saved it as, it'll pull it up. Okay. If you still need help with that, you could always ask me and I'll help you figure it out. Okay. Compare the calculations displayed in GeoGebra with the calculations you completed in parts A through D. Look in the Algebra margin tool. Do the results in GeoGebra match the results you obtained earlier? If not, where do the discrepancies occur? So I don't know what they're talking about with the algebra tool. So like, for example, this line, that's the line that we found here. They got this, but that's the same equation we got earlier. It's just written in a different form. So we might want to say that the equations are the same, but they are in a different, yeah, easy peasy. You've seen two methods for finding the area of triangle ABC using coordinate algebra by hand and using geometry software. We really just use the geometry software, to be honest, but that's okay. How are the two methods similar? How are they different? Why might coordinate geometry be important in making and using geometry software? Okay. The two methods are algebraically the same. Using the geometry tool, or we'll just put GeoGebra. That's the name of the geometry tool. Using GeoGebra, I said the twice. Using GeoGebra, we are able to find the area and necessary side lengths very easily, as effortlessly. You can get the area too. So from GeoGebra, if you go on here, you can look at this and go to the area, click on area, click on the triangle, and it gives you the area right there, which is the same amount that we calculated earlier. Remember, we got 3.49, essentially 3.5. Let's see. Why might coordinate geometry be important in making and using geometry software? We can check our answers. By using coordinate geometry, coordinate algebra, to make sure. Now we don't need to put that. Using coordinate algebra. All right, that's good enough. They give a big old explanation. They don't need all that. Next. All right. Please follow along as I read out loud. Area of a polygon. In this unit, you learned about finding the area of triangles and rectangles using coordinates. But there are many more shapes than just triangles and rectangles, and these shapes often can be relatively complex. You can still find properties of such polygons by dividing them into an arrangement of simpler shapes, polygons that you're familiar with. When a two-dimensional figure is composed of smaller figures, its area is equal to the sum of the areas of the smaller figures. When finding the area of a polygon, it is helpful to know that any polygon can be partitioned into a series of triangles. You will use GeoGebra to partition a polygon into a set of triangles. Go to this link and complete each step below. All right, well, the way they worded that was terrible. Wow, are they really trying to make you understand, or they're trying to confuse you as much as possible? Sounds like they're trying to confuse you. All right, part A. So basically, when you click on this, and it'll make sense when I explain it, you'll see you have 3 polygons here. And what we can do is it's kind of hard to find the area of this thing, right? Like if I want to know how many squares are in this, well, you have 4 whole squares, but then everything else is like a partial square, right? Well, here's a full square, so 5 full squares, and then everything else is a partial, and you have to think well, maybe these 2 together can make a full square. Maybe these 2 together make a full square. It's hard to tell, right? It's hard to tell exactly how it's all cut up. But what we can do is kind of cut this into shapes that we are familiar with. So go to the segment tool here, segment, and probably the easiest way to cut this thing up, I would probably cut from here to here. Now notice we could just find the area of this triangle. Well, that's easy because you do length times width and then divide by 2. So that'd be 3 times 1 and then divide by 2. And you can find the area of this triangle right here. That's easy. Well, can we do that with some of the other parts? Yeah, certainly. We can cut this into a triangle like so. Find the area of this triangle. And then maybe like this. And so what we do is find the area of each of these 4 triangles and then add those together. So instead of just trying to find the area of the whole thing, you can split it into a series of triangles and then find the area of each of the triangles and add that together. This triangle would have a base of 3 and a height of 1. And you would use that formula for the area of a triangle, base times height divided by 2. Find the area, same here, same here, same here. So same idea for each of these triangles. And then just add those areas together. Let's do something similar here. Cut this thing into triangles. You can use that here, here, and here. So this one would have 1, 2, 3, 4, 5 triangles. And we would just find the area of each of those triangles and add those areas together. All right. I want you to cut this one up into shapes that you can easily find the areas of. Okay, you could use triangles or rectangles. Cut it up just like how I did with these ones. Once you have the 3 of them, you're going to make a screenshot. Don't forget to finish the 3rd one. I didn't do that one for you. And make sure the image ends up on this. All right. Next. Think back to task 1 of these lesson activities. Finding the area of a polygon using only coordinates can be tedious. Fortunately, you do have access to additional tools that help you find the area of a polygon while following the same basic methods. This is especially helpful when polygons are irregular or have many sides. Next, you will use GeoGebra to find the area of a polygon divided into a set of triangles. Go to area of a polygon and complete the steps below. So we're going to go to this thing. And we want to split this thing up into triangles that we could easily find the area of. So go to the segment tool again. And we're going to start making this into triangles, like so. Okay. I think that looks pretty good. And we need to find the area of each of these. And then once we find the area of each of them, we can add up those areas together. So let's go ahead and zoom in a little bit here. let's go ahead and right click on this. I'm not going no, I don't want to do that. Okay. Let's see here. Maybe, all right, go to segment tool, and let's just make each of these triangles. So now we have this triangle. Actually, I don't want to do that. Do it that way. Go to this one, the Polygon tool. Let's try that. Here, 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 here. And let's separate each of them into their own polygons. So this one, click, 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 creating the triangle. Click, click. Here, here, create that triangle. And then this, create triangle AGB. Okay. Now, go to the area tool, and we're going to click on each of them. And there you go. This will give us the area of each of these. And then to find the area of the total object, that initial weird object we had, you just add up all these areas together. So we want to take a screenshot. Take a screenshot. Let's with our snipping tool or a screenshot. Copy and paste it onto there. And we want to show the areas of each of them. So I know this is kind of tedious, but we're going to put the areas of each of them. So the first one was area of, and we split this into a few different triangles, right? So we're going to put area of a few times. How many triangles did we put it into? 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. Perfect. Okay, so now let's go back to this one. The area of triangle, and let's talk about this triangle right here. See, area of triangle EDF is 1.1. Or sorry, just 1. That wasn't zoomed in enough, I guess. So the area of triangle EDF was 1, or is 1. So we're going to put triangle, and you could use this right here, triangle. And it was EDF, and that equaled 1. Okay. And now you can see it shows up like that. The area of, and then the next one, let's go ahead and do this one. BDC is 1.5. Area of triangle, BCD. Equals 1.5. All right. And so on and so on. So I want you to do that for each of the triangles that are in this. All right. So there's triangle DGF, triangle DGB, and triangle AGB. And put the areas of each of those on this. And don't forget the screenshot. Don't forget the screenshot of this. Put that there as well. And then we could find the total area. So the total area is, and what you're going to do is you're just going to add up all the areas from this. So just add up all these together to get the total area. You're going to put that there. All right, I hope that makes sense. If you're confused, well, you could always ask me for help later. All right, moving on. Part C. In Part B, you use a combination of GeoGebra tools and manual calculations to find the approximate area of the original polygon. Now try using a more advanced area tool in GeoGebra to verify your answer in Part B. Which method do you choose? So we were actually supposed to do all that by hand, but we chose not to. So let's just pretend we did it by hand and then go ahead and do this. Say that we did it by hand, and and then we did it with GeoGebra. And I want you to notice also, if you go back a few steps, and before we even started, you could just go to the area tool, click on this, and it gives you the whole area. Wow, look at that. So, yeah, I know. But so we could say, which method do we choose? Well, we definitely prefer, or I guess I should say I in these, right? I preferred to use the area tool in GeoGebra rather than calculating by hand. The areas, so you'd say whether it is calculated by hand or with GeoGebra, the area is the same. Okay, good enough. Moving along. All right. Parabolic reflectors. In flashlights, the reflector that directs the light from the bulb is parabolic. If the center of the bulb is placed at the focus of the reflector, then all the generated light will be directed forward in a concentrated beam. In a parabolic reflector, taking a cross-section of the reflector through its central axis will create a parabola as shown in the diagram. All right, and you can see that here's the focus. A manufacturer is designing a flashlight. For the flashlight to emit a focused beam, the bulb needs to be on the central axis of the parabolic reflector, 3 centimeters from the vertex. Write an equation that models the parabola formed when a cross-section is taken through the reflector's central axis. Assume that the vertex of the parabola is at the origin in the XY coordinate plane, and the parabola can open in any direction. So for that, we're going to actually go to Desmos. Desmos graphing calculator. So desmos.com, and you can click on the graphing calculator here, or desmos.com/calculator will get you there. All right, now we want a parabola. Now it said that this parabola, we want, it doesn't matter which direction it opens, but they said they want the vertex at 0, 0. So if you just have the simplest of parabolas, y equals x squared, notice it produces a parabola with the vertex at 0, 0. Okay. Now, I do want to mention that for a parabola, the general form you're going to have is y equals 1 over 4a x minus h squared plus k. Now, I hope you've seen this before, but if not, I'll briefly explain. Do they use A or P? I want to know. Yeah, P. It's been a while since I've done this, so Excuse my mistake. Let's put P there. All right. So P is the distance from the vertex to the focus. So this is the distance from the vertex to the focus. All right. And H and K are the coordinates for the vertex. So this is just the vertex. These are the coordinates, X and Y coordinates for the vertex. So if we look at our, if we looked at what they are asking for, let me close this and this, leave, and this one too. If we look at what we're asking for, we want the bulb needs to be on the central axis of the parabolic reflector, 3 centimeters from the vertex. So we want the focus to be 3 centimeters from the vertex. Well, that means that tells us P. P is 3 because it needs to be the distance between the vertex and focus. It says it needs to be 3 centimeters. So our P is 3. So that's going to be 1 over 4 times 3. I'll just write that as 1 over 12 because 4 times P and P is 3. So 4 times 3, 12. All right. And they said they wanted the vertex at 0, 0. So because the vertex is 0, 0, that tells us our H and K are 0 and 0. So X minus H is X minus 0 squared plus K, and K also is 0. So this becomes Y equals 1 over 12. X minus 0 is just X, and it's squared. I don't need to put the plus 0 because plus 0 doesn't really, well, it doesn't add anything, literally. So this is the equation we're looking for. And I want you to show this work in the equation editor on this. So use the equation editor, put that there. Show all this work. Now, what does this graph look like? So let's go ahead and graph it on Desmos so we can get a good look. So the only thing we need in the front here is a fraction, 1 over 12. All right, so here's what our parabola that we're looking for. This is what it looks like. So this one would have a vertex at 0, 0 and a focus at 3 or 0, 3. All right, cool. Now find the equation of the directrix of the problem found in part A. So something I didn't say about P is that P is the distance between the vertex and the focus, but it's also the distance from the vertex to what's called the directrix. The directrix. The directrix. So since the distance between the vertex and the focus is 3 in this case, well, that means the distance between the directrix and the vertex is also 3, but it's 3 in the opposite direction. So the directrix is going to be 3 away going down this way. So it would be this line, this horizontal line at -3. In other words, the line y equals -3. So here's our directrix, and it's y equals -3. Okay, so we would put the directrix is y equals -3. Y equals -3. I guess we could put something like the equation for the directrix is y equals -3. Part C. Based on feedback from an independent research firm, the flashlight manufacturer has decided to change the design of the flashlight. The reflector now needs to extend 4 centimeters past the center of the bulb as shown in the diagram. In the new design, how wide will the reflector be at its widest point? So it's 4 above, you can see it here, it's 4 above the focus there. So it's going to be here, like this. And they want to know what's the distance there. Well, we can go ahead and let's go back to Desmos here. And let's go ahead and draw that line that they had. And we know that the focus is at 3. And so 4 above that would be at 7. So let's go ahead and make another line, y equals 7. It shows the cutting across here. And they want to know what's the distance from this point to this point. Now, as you can see, this point is at negative 9.165, comma 7. And this point is at positive 9.165, comma 7. And what do you suppose the distance between these 2 points would be? Well, it's pretty simply, it's just 9.165 times 2. 9.165 times 2. Because the distance from here to here is 9.165, and distance from here to here is 9.165. So the total distance across is 18.33. And they put a bunch of words like, I don't even know, and blah, blah, blah. Okay. And that's it. All right, I hope that all made sense. But if you still need help, with this activity, it didn't all make sense, you didn't get it all down, you could always pause, rewind the video, watch it again. But if you want my personal help, you can, of course, always email me. And my email is ttrigg@ofy.org. All right, and I guess that's it. So that's the end for the Unit 7 activity. And I will see you guys with Unit 8 when you get there.